Okay, so now we kind of switch gears completely into cosmology. And for this first one is two very conceptual problems. First one is just talking about expansion versus peculiar velocity. So we're obviously assuming that we're in a FLRW universe, so it's a expanding universe. As the galaxies typically have some random peculiar velocity relative to the overall Hubble expansion, assuming the galaxy distance and redshift can be measured exactly, and the typical root mean squared peculiar velocity is 600 kilometers per second. How far away would the galaxy have to be before it could be used to determine the Hubble parameter h0 to within 10% accuracy? If the true Hubble parameter is assumed to be 70 in this case. So pick the middle ground between cosmology and astrophysics. Nobody gets pissed off. Okay, so for this one, you just start by defining the physical velocity, because that's what you'll be measuring. So if you measure the galaxy, measure like a galaxy in like a galaxy survey, you're not going to know what velocity, which velocity is which. You're just going to measure one velocity, and that's the actual physical velocity it's moving at. And this one is defined as just the time derivative of the physical like distance, not distance, sorry, the physical like kind of spatial coordinate. And this physical spatial coordinate, PHYS is just defined as the A times the R, and R here is the coordinate distance. Either you think of the coordinate distance or like as the co-moving coordinate. So as the universe expands and this A scale factor changes, physical distance change, but the coordinate distance stays the same. So it's like co-moving distance, coordinate distance, however you want to think about it. But okay, putting these in here, then you see that with chain rule, then you just end up getting A dot R plus A R dot. Dot is just the time derivative dt. And now just doing a little bit of algebra manipulation, just adding an extra A in the denominator here, and then putting that here together. And then plus AR dot. Then we can easily associate this thing is the Hubble rate, the Hubble parameter, so H, and then this thing is just the physical distance, so R phys. And this, it's like the coordinate velocity being redshifted. So it's like kind of like a physical velocity, but then you're only redshifting the velocity locally as the coordinate. So that's what you basically call the peculiar velocity. EPEC. So yeah, that should be pretty standard. You should have seen it in the lectures once. So now we see that if we measure the physical velocity, then depending on where we are, there's going to be some Hubble component and some peculiar component. And when it says you want to measure within 10% accuracy, you want this term to be dominating. So if this is a dominant term over this term, then when you measure the physical velocity, you can be sure to say, okay, within some uncertainty, what I'm seeing is this Hubble flow rather than any peculiar velocity contribution. Whereas if you're very close to the object and you're seeing a large peculiar velocity, then you don't know how to separate these two out. Then you can't say much about how much of it is contributed by this H. So this is equivalent to saying if V peculiar on the RMS peculiar velocity divided by H phys is less than 0.1. So if I'm standing somewhere and I'm looking around and the peculiar velocity compared to the Hubble flow is less than 0.1, then this is going to be dominating by at least 90%. So when I observe some physical velocity, then I know by within 10% certainty that majority of this is going to be contributed by the Hubble flow component. So this is going to be a condition to allow us to measure this within 10% accuracy. And now we just have to rearrange this. So let's just say that this is like find a threshold. So let's call this equal to find like the minimum requirement. So this is the condition. Then R physical will have to be equal to 10 times V peculiar RMS divided by H. And because I'm standing as an observer at my local place and I'm looking at something else, so the Hubble I'm going to see is fairly local still. So it's still going to be the Hubble rate today because it's where I am. So we can label this as H naught. If you're looking at something extremely, extremely far away, then maybe not, but this is still fairly okay. So within approximation, and putting in the numbers that we have here, so 10 times the RMS peculiar velocity, 600 kilometers per second, divided by a Hubble rate of 70 kilometers per second per megaparsec, and that's approximately 86 megaparsecs. And that's a fairly okay, that's a fairly good approximation, because if you look at the homogeneity scale of the universe, so 100 megaparsec, so on scales of 100 megaparsec, the universe is homogeneous. Okay, statistically homogeneous. And the expansion is really like a homogeneous expansion in FLRW metric. So you want to be looking at a scale that is going to be like statistically homogeneous enough for you to apply the FLRW metric in order for the Hubble rate to be measured accurately. If you're looking at some very local region, then you break the FLRW symmetry, then you might not be actually seeing any Hubble expansion at all. So yeah, this approximation is pretty good compared to like a actual physical value that we can reference to. Any questions about that? No, all good. Okay. Then let's move on to the next question. Ober's paradox, named after Heinrich Wilhelm Ober. It's the observation that in an infinitely large and infinitely old universe, the sky at night will not be dark. Consider a static infinite universe filled with identical stars, each of radius capital R, distributed evenly but randomly with average separation L. Show that along any line of sight, an observer will see a star at an average distance given by this. So, okay, along any line of sight and the stars are kind of randomly distributed, then you can imagine this to be a mean-free path question. So it's kind of similar to if I had like a random distribution of particles, and then I put a test particle going through this distribution. What's the average distance this particle can go before hitting one of the other particles? So similarly, if these are all stars and I'm an observer standing here and I fire a test photon out, what's the average distance this photon can travel before it hits a star, reflects back and tells me I've seen a star? So this is exactly the same setup as other mean-free path questions. So then we can just use the mean-free path equation where D is equal to 1 over the number density times the sigma, which is the cross-section. Okay, and since the stars are distributed with average separation L, then we can say that the number density is going to be given by just 1 over L cubed. So it's like 1 over the average volume of that you'll find a single star. So then 1 over L cubed will give you the average number density. And the stars, they're just going to be solid round objects, assuming they're spherical with radius capital R. Then the cross-section will just be a hard sphere cross-section. So it would just be pi capital R squared. And then now putting into here, then we just get 1 over n, so we get L cubed, and then in the bottom, pi R squared. And that's exactly what we need. QED. I'm not sure if it counts as a proof. Any problems so far? No, all good. Okay, then for part B, each star shines with a luminosity L, and at a distance R produces an energy flux per unit area of this phi star equals L and 4 pi r squared. Show that the total energy flux per unit area on Earth is given by this. Okay, so we are standing on Earth here, Earth, and we're assuming that we're kind of like surrounded on all sides by stars because the stars are evenly randomly distributed. So it's going to be like a completely isotropic and homogeneous distribution. Then technically the infinite number of stars, but if we knew where every single one of the stars are, then we can easily find the total flux on Earth by simply just summing them up. So it's just the sum over index I indexes over all of the stars that are possibly out there. And you have L contribution from each star, but then it's diluted by 4 pi r squared, depending on how far away this star is. So their power is going to be diminishing as the intensity travels to get to us. So if we knew where all the stars are, then we can simply do this. But the problem is that we don't. We don't know Ri. And there are also infinite number of this. So this sum is going to be not actually computable. So the similar equivalent way to doing this is just to integrate over a luminosity density. So if we kind of like imagine a large enough universe, and in this case, the infinite universe, so it's actually fine. And on an infinite universe, then all of the stars are going to be distributed. And if we zoom out to a far enough scale, then it's going to be kind of distributed like a continuum. And each one of them is going to have some kind of luminosity contribution. So the whole thing becomes like you can integrate over the density, over the entire volume of the entire universe. So in this case, we can write this luminosity density as the contribution from each star. And yeah, remember this one is a function of R. And given the total number of stars of all the stars in the universe, because this is per star, and then integrating over all of the volume of the entire universe. Okay, this integral is still like not immediately obvious how to do because this thing is still an infinite volume. And yeah, this n is also, as far as we know, in an infinite universe with a uniform distribution, this is also infinite. So we want to shrink this problem down to something that's finite and we can calculate and be sure that it will converge. So the way to do it is to go back to the previous question when we had, on average, this is the average separation of stars. And we know the number density of stars. So we can rewrite this density as the same contribution from per star. But rather than over the entire universe, I'm going to go through the number density over the finite average volume. The average volume is given by like the d cubed, d given by the previous one. So I'm just looking at one average volume where I know the density in that volume. Okay, so now that we can do this, then we can go ahead and sub in all the things. So this phi star will be L divided by 4 pi r squared. N is 1 over L cubed. dV is going to be just integrating over the volume. So it's going to be a 3D integral. But we know it's kind of like it's spherically symmetric because it's isotropic in every direction. So we don't have to integrate a solid angle. We can just take out a 4 pi. And we only integrate over the radial direction, r dr. And because we're only going over the average distance volume, so this radius, we're just going from 0 to d. Okay, then this thing is pretty easy because almost everything cancels out. So you just get 0 to d, L on L cubed, dr. These actually don't depend on r, so it's just going to be d, L on L cubed. Okay, and then we sub in the definition we had for d previously. Then this will equal L cubed on pi r squared, L on L cubed, and that equals L on pi r squared. And that's what we want. All right. Okay, then for part C, argue why this should be equivalent to the flux one would get if each point in the sky was as bright as a star. So if each point in the sky is as bright as a star from your perspective, then you know how if you look up into the sky and then you take a survey, then it ends up mapping to like a sphere. So it's kind of like you're looking up in the sky is equivalent to looking into like an inside out sphere. So like looking at an inside out sphere. And if you're looking at the inside out sphere and it's going to look at just like a sphere, and if every single point is as bright as a star, then it's going to be equivalently just like you're looking directly at a star. And that works exactly the same, because if you're looking at any single point, we told before that the star shines with the luminosity per unit area given by this. And you're looking at an entire, you're looking at the entire star, then this is a bit more annoying to explain than I expected. Let's see if I can phrase it better. No, I don't really think so. So you, does it make sense? So you're looking at the sky, and the sky looks like a sphere. And if every single point on the sphere is as bright as a star, then the whole thing would just look like a star, because the whole thing is a sphere and every point is the same as a star. It sounds really circular, but yeah, because this part is not, I guess it's not very clear that the sky was as bright as a star right up at you in a sense. So if I was looking directly at a star of radius r, then obviously the total luminosity, which is equal to L equals pi r squared. Does that make sense? I feel like this is one of those things that's like, it sounds obvious, but then becomes really difficult to explain. Or you can just think about it like locally at a single point is as bright as a star, and everywhere you look is the same. So it's just the same as if you're just staring right at a star. Yeah, kind of. I guess the size doesn't matter, because it's asking for like the flux, and the flux per unit area is this. Then I guess the weird part is, why is this radius r? Okay, so yeah, I think to clarify a bit is that another question. So it looks like we're inside a star looking at its surface. No, it's more like if I turn the star inside out, so the surface is surrounding you and you're standing right in the middle, looking at every direction at the surface of the star. Yeah, so what was I going to say before this r? Oh yeah, sorry, yeah. So the flux at some large distance away is going to be 4 pi r squared, and this r is like distance from the star. But then if you're right up at it, so if you're right up at the surface of the star, and that's equivalent, that is exactly what it's saying, is that if the point on the sky is as bright as the star, then you're kind of like right up against its surface. Then in this case, this would just be L of pi r squared, because your distance 0 from the star. Yeah, so I think the best way to think about it is just that the surface of the star is being plastered right on top of the sky, and you're staring right at it. So it's kind of right in front of your face. So it's like an inside out star, and the surface is right there. Oh, okay, actually, that's not correct. Technically, this is pi equals L over. So this r is the distance from the star. Then if you right up at it, then I equals 0, then you get that. All right, cool. All right, hope that makes sense. Okay, so the next part. So Bob says, perhaps the night sky isn't bright because all those stars are hidden behind clouds of dust, and that's why we cannot see them. Why does Bob's argument not work? So Bob's arguing that there's basically a lot of interstellar dust, and the dust is covering most of this, the luminosity, so then we can't see them. Dust in like astrophysics is basically hydrogen gas, or sometimes okay, it could be helium as well, or like some light elements, helium gas. But a majority of it is hydrogen gas. So a lot of times, if you have stars like go supernova and it blows out a lot of the material, then this material kind of lingers around as gas before it gets to form another star. Or an early universe where most of the things are still like kind of before it got to form stars, then they just hang around as hydrogen. So if they're hydrogen gas, then this argument is very easy to dismantle, because if I had a star here and is emitting light towards me, and here is Earth, and there's a like dust in the middle, or gas, hydrogen gas in the middle, then what this gas does is that it absorbs the light, and then the hydrogen absorbs the light and holds the energy, and then it would eventually emit the energy again. So think about it just as like a photoelectric effect kind of thing, where the hydrogen's electrons will absorb the photon, but then eventually this electron is going to jump back down and release the photon elsewhere. So this dust, when it's very cold with like almost no energy, then it might be able to absorb quite a lot of this light from the star coming over here, and I won't see anything for a while. But given enough time, then this dust is going to be holding so much energy that it's going to give out, like start radiating like a black body. So eventually, with enough energy absorbed, it's like black body radiation. So it's going to eventually radiate back this light that it initially absorbed. And in a universe that's infinitely large, then it's going to be infinitely old. Then it's going to have plenty of time to absorb enough energy and then emit it, as some of it at least is going to be in my direction. Then on Earth, you'll eventually see these lights come through anyway. So maybe in the first couple of like 100 years that these dust can hold enough energy that you can't tell on Earth. But in an infinite universe, this argument doesn't work, because eventually all the dust will be thermalized, and all the dust will then eventually release back the light, and it will just as if they aren't there anyway. So Okay. All right, question part E. In our universe, the average mass density corresponds to about 1 hydrogen atom per cubic meter. And the mass of a hydrogen atom is given by mH, approximately 1.7 times 10 to the minus 27 kilograms. Assuming that this mass was concentrated entirely in stars similar to the sun, with mass, the solar mass, and radius times 10 to the 8 meters, show that the D, so this D is the same, this D, this average distance. Show that the average distance is equal to this. So if every single mass in the universe is concentrated, and okay, then we basically can first say, since this is per cubic meter, then this is actually gives us the density straight away. So density of hydrogen is just equal to 1.7 times 10 to the minus 27 kilograms per meter cubed. If not, then you can always just work out how much given the density. So given the density here, and we know that all this density has to be concentrated into a star. So we know the mass of an individual star. So it's similar saying, if you know the density of some matter and you know the mass of an individual particle of that matter, then you can find the number density. So number density is in general given by the density divided by the mass of an individual particle. So in this case, the number density of suns or solar mass stars is just going to be the energy density of the hydrogen, or mass density of the hydrogen, divided by the mass of a single sun. So that's equal to 1.7 times 10 to the minus 27 divided by 2 times 10 to the 30. And that will give you a fairly small number, so about times 10 to the minus 57 per meters cubed. Okay, so that gives us a number density. And before, when we worked out D, we were just saying is equal to n sigma. So then this just equals to 1 over n pi r squared. And if we want to just make it for this particular scenario, then it's obviously the number density of solar-like stars and also the radius of a typical solar sun. So now that we have the n solar, then we can just put that in. 1 over 10 to the minus 57 pi solar radius is 7 times 10 to the 8 squared. And that's equal to 10 to the 39 meters. So if I convert that in megaparsecs. Nothing not working. 23. Okay, whatever, doesn't matter. You don't. You just have to figure out yourself. Okay. Anyway, so then, given that D, then for how long must the static universe and all the stars in it have existed for at least for light to reach us from this distance? Compare this to our universe, where the first stars formed about times 10 to the 10 years ago. So the average distance of stars are about times 10 to the 39 meters. And if the universe would, I don't know, formed at some point in time, and then we wait, how long do we have to wait for the light to travel to us in this universe? And it's static, so it's not expanding. So we don't have to worry about any of that FLRW business. We just have to calculate how long does it take for light to travel this distance. So then the time it travels is just the distance divided by the speed of light. So 10 to the 39 meters divided by 3 times 10 to the 8 meters per second. So that's approximately 3 times 10 to the 30 seconds. And if you convert that to years, that's about 10 to the 23 years. So if we are living in that universe, then at this point, the entire sky should be entirely dark. So no light would have reached us. At this point. Yeah, so that's it. Any questions? I suppose we could fit more questions in this tutorial. All right, if not, then I'm just going to stop recording.